So I gave tips on how to solve forces problems, but I thought maybe you want a like a visualization of what that would look like. So I wanted to cover what's the best way to push a crate. So I want to maximize the acceleration of this crate. So how do we analyze that acceleration? Let's look for it. First thing we could do, draw a free body diagram. So I'm going to draw one for the crate. Let's say the crate has a mass of m, and I'm going to say it's uniform density. So the mass is evenly distributed, which would place the center of mass right here. So we'll have gravity pulling down. We will also have a normal force pushing up. And let's say that we are, maybe the crate is larger than us and we are pushing at an angle. So it's just a generic push. Maybe the floor is carpet, so we have a frictional force. So we'll just call it kinetic friction. We'll say we can get the box moving. It's now moving. And maybe we can estimate the angle at which we were pushing at, so the angle above the horizontal. So how do we analyze this in such a way that we can kind of figure out our expected acceleration? Because we want to maximize this acceleration. Well, we've drawn a free body diagram. Next thing to remember is we can get acceleration from either kinematics or Newton's second law. In this case, I've given no position or time data, so we probably want to use Newton's second law. My second tip was to remember there are two equations with net force. There's second law and the definition of net force. And by definition, net force is equal to the vector sum of all the forces acting on the object. So let's take a look here. If we are accelerating forward, then we can see that the net force should be equal to the x component of our push plus, well, not plus, but minus the friction. And the reason why I say the friction is the negative, my other tip would be to make your acceleration positive. That way your net force is always kind of intuitive. So here we have net force, which is going to be equal to ma according to second law. The x component here will be f cosine theta minus mu times the normal. But take a look here. The normal will not equal the weight because we have a y component to our push. So I'm going to get rid of this, just to kind of clean it up. Because remember, we do not put components on free body diagrams. So we can rewrite this as ma is equal to whatever our x component is minus the friction, but we can replace this normal here. According to our y data, the gravity is the only thing pointing down, and if we're in equilibrium, if this crate's not accelerating up or down, the gravity should be equal to the normal plus that y component. So we get mg is equal to normal plus f sine theta. So the normal, let me kind of give me some more room over here, ma f cosine theta minus mu, and the normal we can rearrange. So normal here would be mg minus f sine theta. And we get, we can distribute the mu. Minus mug plus F sine theta. Divide everything by the mass. And so we can see here, if we're pushing upward, that will help us by reducing the amount of friction. Because again, it has to, the upward forces have to equal the weight. So if we add an upward component to our push, the normal would go down. The only issue here is if we can only push so hard, that's going to take away from the forward component of our push. So let me kind of illustrate this here. Let's just get rid of that layer real quick. So if we can only push with a force of F, if we push straight across in this scenario, we will get our full force forward, and we'll get a frictional force that uses a normal that is equal to the weight of the box. If we aim upward with the same force, notice that the forward component is not as great, but the frictional force, since we are pushing up on the box, we're lifting off the ground a little, the normal force here would be less than the weight. So kind of there's probably an angle where we get a bit of a trade-off. I'll leave that derivation for you. Might be easier with a little bit of calculus. What we definitely want to avoid, though, is if we're pushing down on the box at an angle, then the normal force has to not only equal the weight of the box, but it also has to equal the downward component of our push. So that would increase the friction. So we're getting less of the forward component from our push and more friction. That would be the worst case scenario. And that's just kind of our sample problem here. We successfully found the acceleration in that scenario, and hopefully that helps. And that's all I got.